Okay, so electron configuration for calcium, pretty simple. Just do what we did last time. We're going to start with the 1s, and same thing as before. 1s has 2 boxes, so it's going to be 1s2. This section right here will be the 2s, and there are 2 boxes. So it'll be 2s2. 2p right here has 6 boxes right here. So it'll be 2p6. We got 3s right here, so that'll be 3s2. Right here, we got 3p, and then there's 6, so 6. And calcium is box number 2 in the 4s section, so it'll be 4s2. Okay, easy peasy, right? Okay, so this right here is called the electron configuration. So let's kind of label it. There is another type of configuration that you might be asked to write. It's actually a lot easier and shorter. It's less writing, so I personally prefer it. It is called the noble gas configuration. Okay, noble gas configuration. Okay, so noble gas configuration is another way of writing the electron configuration that the AP test might ask you to write. If it just asks for the configuration, you can choose which one to write, but sometimes they specify, write the noble gas. And so if that happens, this is how you write it. So the noble gases are this last column right here. So you guys should have seen this in your reading, I think in like the first week. But these are the noble gases. Basically, these ones right here. And if you notice, a lot of the electron configuration, most of it is just like the same, right? The base is the same. And so what they do instead is they look at the noble gas that comes right before your element. So if you look at calcium right here, the noble gas that comes before it is argon. So argon is this entire section right here. Argon's electron configuration is all this. So instead of writing all of that, what we can do instead is we just put brackets and write Ar for argon. And the only part that's unique to calcium is the 4s2. So we just write 4s2. Okay, so a lot easier, right? Way less writing. You literally just need to find the noble gas before it and then just count till there. Okay. All right, so let's do a quick practice with noble gas, and then we'll move on to the next rule for this. Let's have you guys try. Sulfur. So see if you can write both the electron configuration and the noble gas configuration for sulfur. I'll give you guys about 2 minutes to do that. I am. All right, guys. So I got the electron configuration for sulfur up there for you. It is in the 3p section, and it's box 4, so it ends with 3p4. Okay. Now, to do the noble gas configuration, we got to look at the noble gas that comes before it. Now, sulfur is right here. It is closest to argon, but we got to use the one before it. So we're going to go all the way back to neon. So this section right here, neon, is 1s2, 2s2, 2p6. So this gets replaced with neon. However, neon does not have 3s, so we have to include 3s2 and then 3p4, and that will be the noble gas configuration for sulfur. Okay, so always look at what's before the noble gas before your element, and whatever that noble gas does not have for its own electron configuration, you just add it on top of it. All right, any questions on that? Hopefully pretty easy. All right, so we're gonna go over the last type of electron configuration, and it's going to be the elements that are in the middle right here in the D section. Okay, the D section, because the D section is a little bit different. It operates with a little bit different rule. So we're going to take a look at chromium right here. And if you look, chromium is very similar to calcium, right? So we're going to just do the noble gas configuration just for the sake of time. Chromium, the noble gas right before it is argon. So we can skip the first 3 rows and just write argon. Okay, and that's going to be 1s2, 2s2, 2p6, 3s2, 3p6. All right, so we got up to argon, so let's start counting from here. So if you remember, this section is the S subshell, right? So we got to do those. So it'll be 4s2. And if you remember this section right here, we call this the D subshell. Okay, so we're going to have a number and D. Now, I know chromium is in the fourth row, but for the D section, you always drop one row. So this is actually going to be 3D. Okay, and it has to do with the energy levels. Well, we're actually going to see a diagram for a second, but just trust me for now. So chromium is going to be in the 3D. If you're looking at like yttrium right here, this is in the 5th row, but it'll be in the 4D subshell. So you just drop it one row. That's the thing you need to remember about the D subshell. Okay, so it'll be 3D, and then you just count the boxes. 1, 2, 3, 4. So it'll be 3D, 4. So this is chromium's noble gas configuration. Okay. All right, let's do one last one. This will be the last electron configuration that we do for now. So let's have you guys do silver. Okay, Ag. Ag is right here. And you guys can just do the noble gas configuration. You don't need to do the entire electron configuration. Just try the noble gas. We'll go over it, and then we'll move on to the next topic. All right, guys. So noble gas configuration for silver is krypton, and then 5s2, 4d9. Okay, and that's pretty much it. We're not going to look at the ones at the very bottom of the periodic table. You shouldn't get the electron configurations for that, so we're not even going to talk about it. Okay. Okay, that is writing the electron configurations like this. Now, there is another type of electron configuration problem that you'll see on the AP Chem exam. And it's going to be a diagram. So I'm going to scroll down, and we are going to talk about something called quantum numbers. And basically, these are the, I guess, ID numbers that that electrons in an element can have. So we've actually talked about 3 of them. Okay, so the first one is the shell, and this is like the 1 in the 1s, or the 2 in the 2p. The second one right here, this has to do with the subshell. So this is going to be the S, the P, the D. And then the number that comes after it, that is the third one right here. And that's the one that we've been talking about that we put as the exponent. Okay. Now, when we look at electron configuration, it's basically telling us the energy level these electrons are at. And this diagram right here is basically how we can visualize that. Okay, so on your paper, I don't want you guys to draw this. We're going to go through it just one at a time. We're going to go through it element at a time. So I'm just going to put up a blank screen. And then I'll kind of explain it as we do the problems. Okay, so we're going to draw the electron configuration. Let's start with the easiest one. We're going to start with hydrogen. Okay, so I do want you guys to get this on your paper. Now, hydrogen, if you look at the electron configuration, it's just 1s1, right? So if we're going to draw the diagram that we just looked at, what we would do is we would just put something on the y-axis that says that energy goes up as you go up in the axis. And hydrogen, its electron is going to exist in the 1s subshell. So we draw a line like this, and we write 1s. Okay. And what we're going to do is we're going to draw an electron on the line. And the way that we draw it is we draw it with these like half arrows. So we draw an arrow like this. And this represents the 1s1 electron that hydrogen has. So this is the electron configuration diagram for hydrogen. And so since hydrogen only has one electron, it exists in the lowest energy level, which is the 1s orbital. And there's one electron in there. Okay. Okay, let's do helium now. So helium is very similar to hydrogen. It's just 1s2. Okay, so if you wanted to draw the second one, what we have to do is we just put a second electron in the 1s subshell. So we put a second electron, but this time we have to make the arrow go the other way. And the reason why is because when these electrons are in an orbital or a subshell together, they have to spin the opposite way because electrons repel each other, right? And so this up and down arrow just represents that they are repelling each other, spinning opposite directions. If you want a really in-depth description of why we do this, then you can read your textbook. But if you just want to learn how to solve the problem, then you can just do this. Okay, up arrow, down arrow. All right, everybody good so far? Okay, so let's just keep adding on to this. So we're going to go on to lithium now. Now, lithium is pretty similar to this, just one up from helium, right? So it'll be 1s2, 2s1. Now, we're going from 1s to 2s now, and 2s is at a higher energy level. So what we're going to do is we're going to draw a line above 1s to indicate that the 2s subshell is higher up than the 1s. Okay, so higher energy level. We still need to draw the 2 electrons that are in the 1s subshell, but it's the same thing as helium. But for lithium, there's a third one in the 2s, and so we just draw an extra electron in there. Okay, so that's going to be the electron configuration diagram for helium. Okay. And again, what this is basically doing is it's helping us visualize where the electrons are and how many are in each subshell and shell. Okay, I'm going to show you guys how to do one more, and I'll have you guys try one on your own. Okay, so next we're going to look at, let's go from lithium. Let's jump up a little bit, and we're going to go to carbon. Okay, so we're going to look at carbon. If you look at carbon's electron configuration, carbon is 1s2, 2s2, and 2p2. So now we're going to go up from the 2s subshell up to the 2p. Now, 2p is going to be even higher than 2s, so we just need to put it up, and we put it off to the right. Okay. Now, if you look at each of these subshells, how many electrons go on each of these lines? What's the max number that can go in there? 2. Yeah, there's 2 arrows that we have here. This one's not full yet, but you can put 2. Now, if you look at the P section for on your periodic table, how many electrons are there in the 2p subshell? 6, right? There's 6 boxes. What that means is since each of the lines can have 2, there are 6 in 2p. That means the 2p has 3 lines on it, because that's the maximum amount of electrons we can put in there. Okay, and then from there, filling it in is pretty much what we've been doing. Carbon has 2 in the 1s, so we draw 2. 2s also has 2. Okay, now we're going to draw for 2p, and this is where another rule, a special rule is going to come in. When you have electrons and multiple lines, so typically in the P or the D subshells, you might just be tempted to just kind of put them together like this. Okay, but you can't do that because if you remember, electrons repel each other, right? They don't want to be next to each other. So one of the rules that you need to know is that if you have electrons, they need to go separate first. Okay, you need to separate them out amongst the lines before you start filling them in. Okay, and this is representing the electron repulsion. Okay, when you fill up all of them, and let's say you have another electron, then you could start pairing them up together. But they're going to want to be separated with each other before they start pairing up. Okay, but this is going to be for carbon. So that's one of the rules you need to remember. Okay. All right, do you guys think you could try one on your own?
Yeah.
Okay, let's have you guys try another one on your own. I want you guys to draw the electron configuration for, let's do magnesium. Okay, so for Mg, actually not magnesium, sorry. Let me go back. Let's do chlorine. I want you guys to try chlorine. So go ahead and try chlorine. Give you guys about 2 minutes to do that, and then we'll go over it together. All right, so for this diagram, I'm just going to pull up my periodic table, and we'll that way we can take a look at it. But if you take a look at chlorine, chlorine is right over here, and it's going to be in the 3p section, right? So we got to draw our diagram going up to 3p. So I'm going to draw my diagram right here. That means we're going to have 1s, we're going to have 2s, we're going to have 3 lines for 2p, we're going to have a line for 3s, and then we're going to have 3 lines for 3p. Okay, and this diagram is on the notes, so if you ever need a refresher on where the lines are, how many they are, you can always look back on that. Okay, so it's in the 3p section right here, and honestly, I think it's easier just to look at the final subshell and just kind of fill in from there. So 3p, it's box number 1, 2, 3, 4, 5. So it has 5 electrons in the 3p section. So 1, 2, 3, 4, and 5. So it's going to look like that in the 3p subshell. Okay, so like I said earlier, always separate the electrons first, and then you can start filling them in afterwards. And then, since you already know everything underneath is filled, you can just kind of plug in each line with these electrons. Okay? So far, so good? All right, let's have you guys try one more, and then, yeah, let's have you guys try one more, and then we're going to use that as our example for the later ones. Okay? Hey, thank you. Okay, let's have you guys try the draw the electron configuration for iron. Okay, so do iron. Actually, I want you guys to do 2 because we're gonna go into the next topic straight instruments. I want you guys to do lithium, which I think we already did lithium, right? Okay, I'm sorry guys, my brain is not there today. Let's have you guys do sodium and iron. Okay, so you're gonna do the diagrams for both sodium and iron. And then we're going to use those 2 as our examples for the next topic. So make sure you guys draw both of them because we're going to be going into the next topic with both of them. Okay. So we're going to start with sodium. So sodium is the first box in the 3s. So we just need 1 electron in the 3s, and then everything else we can just fill in. Okay, super easy. All right, let's go to iron now. Okay, iron, if you take a look, is box number 1, 2, 3, 4, 5, 6 in the 3D section. So it'll be 1, 2, 3, 4, 5, and then you got to pair up one of them in the 3D. Okay, and then everything else you can fill in from there. Okay, everybody good? Hopefully this is pretty easy. All right, now, there is one other thing that the AP test might ask you about electron configuration, and it's going to be about ionization. Okay, so ionization. Oh my goodness. I'm always interested. So ionization, again, just if you guys forgot, make sure you write down the definition, is when you remove electrons from the atom. And we're going to talk a lot more in detail, super in detail about it next unit. But just keep that in mind. Ionization is when you remove an electron from an atom. And so one of the things they'll actually ask you on the AP test is which electron is removed first. Okay? And it's very easy. It's whatever's at the highest energy level. Okay? So if you take a look at sodium, where is the highest energy electron? Which subshell? It's just, which one's the highest? 3s, right? So if it asks you, where would the electron be ionized from Na? You would say from 3s. Okay? And this is actually the reason why sodium's most common ion is Na+. It's because there's 1 electron in that highest energy level, right? So it's going to want to ionize this electron, and then if it gets rid of this, now the shells are completely full and the energy level is stable. And that's why sodium wants to become sodium +1. Okay? All right, so it's the same thing for all of them. So if you look at like beryllium, for example, the electron that's in the highest energy level is in the 2s subshell, right? So you would say electrons are removed from the 2s subshell. Now, there is something that's very different about these transition metals where you have a D block. Now, if you guys take a look at the diagram that we drew and in your notes, it looks like 3D is higher than 4s, right, in terms of energy level. However, it's actually not going to be. So you guys probably want to write this down. And what you want to write down is that electrons are removed from 4s before 3d. Okay, and there's a couple different reasons why. We're going to talk about something called electron shielding and in the next unit. And basically, the electrons in the 3d section have less shielding, and so they're actually held tighter by the atom, even though they're at a higher energy level. It looks like a higher energy level. Again, we'll get more into detail. To solve the problems, just very easy. Just remember, 4s is removed before 3d. Okay? All right. Any questions about that? This is very big. This is going to be on your exam too, by the way, the one that we take in class. I will try to trip you up and ask you to write the electron configuration for an element where you have to remove from 4s before 3d. Okay. All right. So just to kind of make sure we got it, let's do electron configuration for some couple elements. So I want you guys to do the electron configuration for Be 2+. Okay, and I want you guys to do the electron, and you guys can do noble gas configuration, so if you don't want to do the entire thing, you don't have to. I also want you guys to do the electron configuration for Al3+, and also do the electron configuration for, let's do Ti+. Okay, so 3 different electron configurations. You can just write it out. You don't need to draw it. Just see if you guys can get these 3. If you can get these 3 correct, then you should be in pretty good shape for the exam in terms of electron configuration. So try that out. We'll go over it in about 3 minutes. All right, so let's start with Be2+. Now, if you remember, the positive sign means that you lose electrons, right? So typically, Be would be 1s2, 2s2, okay? Or you could do the noble gas configuration and do He in brackets and then write 2s2. However, Be lost 2 electrons, right? So we remove them from the highest energy level, which is the 2s energy level, so we can just get rid of that. So you can either have 1s2 or just write He in brackets. Either way works. Okay, so just keep that in mind. The positive charge means that you are losing electrons from the highest energy level, so you just take them out the highest energy level. All right, let's move on to aluminum, which is pretty much the same thing. If you take a look at aluminum, it's in the 3p section. So you would write 1s2, 2s2, 2p6, 3s2, and then 3p1. Okay. Or you could have done it the noble gas configuration and done Ne in brackets, 3s2, 3p1. However, we're taking away 3 electrons because it's positive 3. So you take away 1 electron from 3p and then 2 more from 3s. So you would just be left with this or just Ne. Either answer would work. This is just the full electron. This is the noble gas. All right, let's move on. The last one is Ti+, and this is the one where we're going to use the rule that we talked about right before we did these. I'm just going to do the noble gas because I don't want to write it all out. But you're going to write brackets Ar, and then Ti passes the 4s section, so 4s2, and then it'll be 3d2, okay? But it is +1, so that means you're going to lose 1 electron from the highest energy level. But we said that we remove from 4s before we move from 3d, so it's going to be 4s1, 3d2. Okay, and that's the trick, and that's what's going to be on your exam. Just remember, take away from S before you take away from D. All right, so the last section is we're going to be drawing these things called Lewis structures, and just very easily, simply put, it's easier ways to draw the atoms than the shell model. Okay, so don't draw this next part. I'm just trying to prove a point to you. But we learned about how each row represents a different shell, right? Now the problem is once we start looking at bigger elements, like for example barium, right? Barium is in the 6th row. So if I asked you to draw barium and you drew all the shells, you would draw 1, 2, 3, 4, 5, and 6. And then you would have to draw 56 electrons in there, which would take forever. And let's be honest, nobody's going to count all that. So instead, what we do in Lewis structures is you draw the valence electrons only. So Lewis structure, you draw only the valence electrons. And if you remember, valence electrons are the electrons in the outermost shell. Okay, and this is okay because the valence electrons are the ones that are interesting anyway. When you combine elements together, it's the valence electrons that allow them to combine. When you ionize, it's the valence electrons, the outside electrons at the highest energy level. Those are the ones that come and go. And so that's why it's okay, only draw valence, because they're the interesting ones anyway. So let's look at our example of barium, and we're going to draw the Lewis structure for barium. It's very simple. You just count the boxes in that row. That will tell you how many valence electrons it has. So if you look at barium, barium is box number 2. So instead of drawing 6 shells with 56 electrons, you would just write Ba, and you just put 2 dots next to it. And that's it. It has 2 valence electrons. Okay. Pretty easy, right? All right, I want you guys to draw the valence electrons now. I'll have you guys draw a couple examples. I'll show you guys one more. I want you guys to draw the valence electron, or the Lewis structure for sulfur, and let's also have you guys do the Lewis structure for lithium. Okay, take like a minute to do that, and then we'll go over it, and then we're gonna add more on top of this. Okay, guys, let's draw sulfur and lithium. So let's start with sulfur. Sulfur is box number 1, 2, 3, 4, 5, 6. So we're going to have 6 valence electrons for sulfur. Okay, very easy. Okay, now just a heads up, when you guys are drawing Lewis and shell models, I highly recommend doing or drawing them in the cardinal direction, so up, down, left, right. If you do it around, you kind of look like a noob, so they'll probably take off points. It's also easier to count if you put them in the cardinal directions. Okay. All right, last one, lithium. It's 1, so it's just 1 valence electron. And that's it. That's the Lewis structures. Okay, now it doesn't stay that simple, unfortunately. There is another thing that we need to keep in mind for Lewis structures, and what we need to keep in mind are elements that are lower on the periodic table. So we're going to take a look at bromine, and we're going to talk about the Lewis structure, how to draw the Lewis structure for things like bromine. Now, bromine is interesting because it's right over here, and there are a bunch of boxes in the middle, right? However, if you remember, this is the D subshell, right? And if you remember, these are actually at a lower energy level. It is in the 4th row, but this is the 3D subshell. So it's actually at a lower energy level in terms of drawing these valence electrons. So when you're doing the valence electrons for things that pass the D section, you just skip the D section. So it'll be 1, 2, you skip this, 3, 4, 5, 6, and 7. So you will have 7 valence electrons for bromine. So just keep that in mind. Things like bromine, iodine, xenon, those are probably the 3 most common ones you'll see. Those ones you skip the D subshell when you're drawing the valence electrons for the Lewis structure. Okay. All right. Now, last thing for the unit, we're going to be drawing the Lewis structures for ions now. So what happens when you start adding and subtracting electrons? I know there's just so much stuff that goes into this. So it's pretty simple. You just need to remember what does it mean when it has an electronic charge. Okay. So we're going to start with the examples that we've actually been doing. And then, we'll finish up with that. So let's start with S. So sulfur's most common ion is 2-. Okay, now if you think about the 2-, the negative sign is basically telling you that you are adding electrons, right? You have more electrons because it's more negative. So that means that S2- has 2 more electrons than S. So S has 6 valence electrons. So you just add 2 on top of it. So instead of 6, sulfur is going to have 8 valence electrons. Okay. Pretty simple, right? Okay, let's go to lithium now. Lithium, its most common ion is Li+. And this is going to be a little bit different because if you look at the charge is positive, right? That means you're going to have 1 less electron than regular lithium. Well, if you look at lithium, this is the This is the Lewis structure, but I'm going to draw the shell model just to help you guys visualize it. This is a shell model for lithium. 2 in the inner shell, 1 on the outer shell. And we just draw the outer shell for the Lewis structure. If we take away electron, again, we need to take away from the highest energy level. So we're going to take it away from the second shell. Now, if you look, how many electrons are in the second shell?
None.
Or there's none in the second shell, which means this thing is going to disappear. And that means Li plus, its new valence shell, is the inside one. And that means that lithium plus is going to have 2 valence electrons. It's going to lose the outermost shell. Okay, that's pretty much what you need to keep in mind. So if you guys want to make a little note just to remember, if you have a cation, cations will basically lose their valence shell. Okay, they basically end up becoming the noble gas before them. Because if you look at lithium, if it loses an electron, it basically becomes helium in terms of the electrons in the shells. Whereas anions, they are going to fill their valence shell. Okay, and this is actually the reason why we have the most common ion pattern we talked about. It's because it makes them similar to their noble gases, the noble gas closest to them, and that's going to allow them to have a more stable outer shell. Okay, and so that's pretty much how you do Lewis structures. That's about as tricky as it's going to get. The tricky ones are the cations. All right, so we're gonna do 2 last examples for this unit, and then we'll move on to unit 8. Okay, I want you guys to draw the Lewis structure for, let's do bromine, so Br minus, and I want you guys to draw the Lewis structure for Ca2 plus. So we're gonna do Br minus and Ca2 plus. See if you guys can get the Lewis structure for that, and then that's it. That's it for this unit. All right, so Br minus, if you guys look, it's an anion, right? It's going to gain an electron. So regular bromine has 7 valence, so Br minus has 8 valence. That's it. Ca2 plus, it is a cation, so it's going to lose its valence electron. So regular Ca has 2 valence electrons, right? Because it's box number 2. But if it loses these electrons, it's going to lose its outer shell, which means it's going to become the noble gas before it, which is argon. And argon has 8 valence electrons, so this is also going to have 8 valence electrons. Okay, that's it. All right, guys, congratulations. That's Unit 7.